let's take a look at refractions. Refractions are quite important. A refraction is what happens when a wave passes from one medium into another. Okay, so here we're going to be dealing with light mostly. So light bending when it goes from glass into water, where it goes from air into water. Right, I've mentioned before, you'll commonly see refraction if you take a cup of water and you put a pen in it or a straw, you'll see it bend. Or you look at your leg when it's under the water in a pool and it'll look like it's not in the right spot. What your body's telling you it should be over there, but it doesn't look like it. But really it is over there where your body says it is. Just that the light is refracting. Now right here you have a barrier. Barrier is where the two mediums meet. Sound waves also refract. So when light hits the barrier, it bends at the barrier. Some of the light is reflected as well. Some of the light is reflected, but usually if it hits at certain angles, most of it gets bent inside. If it hits at a shallow angle, then most of the light will reflect off. So what happens when the light hits the barrier, whether it goes into the other medium and refracts, or whether it bounces off, depends on the angle of the light hitting it. All right, so we're going to do a few examples on here, and we might do a few extra examples that aren't here. So what we have here is we have a diagram of what we're going to be doing with. We've got a light ray, here's our incident ray, and here's our refracted ray. Here's the normal. I called it a barrier. Interface is another word. We measure our angles from the normal. The normal is perpendicular to the interface between the two items. And we send the light in at a certain angle compared to this, and it comes out at a different angle. There is a formula that relates the two angles. There's n1 times sine theta 1, that's the angle for this, equal to n2 times sine theta 2. N's are found down here in our index of refraction chart. The higher the n, the more the light bends. You can see our diamond's got a really high n. It bends light a lot. That's why people like diamond rings, because the light goes into the diamond and bounces around and gets scattered about and kind of reflects all over the place. It's also why cubic zirconia is a pretty good imitation for diamond, because it has a high refractive index. All right, so we're going to deal with this a little bit. Now, you see up here we have the electromagnetic spectrum, which we've looked at in multiple units, and you should have a good understanding of. We've got short wavelength but high energy gamma rays here. We go to X-rays, to ultraviolet rays. Then we've got the visible spectrum right here. This is what we see: violet, blue, green, yellow, orange, red. Infrared, microwave, radio waves. All right, and all of these, every wave actually refracts a little different when passing from one medium to another. Okay, so this is why we're going to get a rainbow through a prism. Because when the white light, remember white light contains all the different wavelengths, when it hits the prism, it bends. But the red bends a little less than the violet. The red bends a little less than the orange bends a little less than the yellow bends a little less than the green bends a little less than the blue bends a little less than the violet. So on this other side, you're going to see all of these different colors of light spread out. So we're going to write this down. Each wavelength bends slightly different. So when you pass light through a prism, the violet bends more than the red, causing distinct lines. Distinct. Oh, for Pete's sake. Bands of color. A rainbow is formed because raindrops work like little prisms. There's a couple of other things involved in the raindrops, but the raindrops work like little prisms, forming a rainbow as well, the typical rainbow. Roy G. Biv. All right, so we've got this refracting. Now we're going to look at what happens when we bend light into materials. All right, so here's our indices of refraction here. So we've got like vacuum has no index of refraction, air has a very slight index of refraction, helium is a very slight, hydrogen slight, carbon dioxide a little bit more than air. But then some of the liquids like water and ethanol, olive oil, slight indices of refraction. And I'm going to need a calculator out so we can do some calculations. My calculator's down to very low battery power. So hopefully we'll get through, because we're going to do a couple more than this too. So the first one we want to do is we want to start with some light hitting interface. And it's going from a low angle refraction. So let's go from vacuum into, let's say, water. Now let's make it air into water. Now in the textbook's going to say you used 1 for air. Because you look at how slight this is here, the 3 decimal places, we just use 1 for air when we're doing our calculations. So we're going from a low to a high. So this is N2, to a higher one. Now let's see what happens to our angle of refraction. So I'm going to call this looks like, let's say 25 degrees. That's theta 1. We're trying to figure out what theta 2 is. So we have 1, 2, 3, 4 variables here. If we know 3 of them, we should be able to find the 4th one. So let's fill in what we know. We know our N1 is 1 for air times sine of 25 is equal to 1.33 times sine of we don't know yet. All right, so we do, oh boy, I sure hope I am on sine of 30. Aha, I can't use this calculator because I don't know how to switch it back into radians. I'm going to have to go to a different calculator. 30 sine is 0.5, good. So I do 1 times sine of 25. And it's equal to 0.4226. And that equals 1.33 times sine of theta. Now I'm going to divide both sides by 1.33. So I divide that by 1.33 to get 0.3177. Sine of theta. Now we use our second function sine button to get our angle. So I use my inverse sine to get an angle of 18.5 degrees. So when it bent, it has 18.5 degrees. That's theta 2. So when we went from low to high, a low one to a high one, it bent to normal. Bent towards normal. Now let's see if we do the other way. If we go from a high to a low, it should bend away from the normal, right? So let's try something that's high. So let's try diamond. Let's get diamond out here. So N1 is equal to 2.42. And let's go from diamond, let's go into water again, where N is equal to 1.333. Let's say that this is our same 25-degree angle, theta 1. So what's going to happen? Well, when we went from a low one to a higher one, it bent towards the normal. So when you go from a high one to a lower one, it should do what? I hope in your mind you're saying you should bend it towards the normal. Okay, so let's see what happens. N1 is 2.42 times sine of 25 is equal to 1.33 times sine of theta 2. So I do my 2.42 times sine of 25. Oh, I did. We get 1.0227 is equal to 1.33 times sine theta 2. Then we divide both sides by the 1.33. So we divide it by 1.33 to get 0.7689 is equal to sine of theta 2. We do our second function sine button to get 50.3 degrees. Right, it bent away from the normal. So this is now theta 2 is equal to 50.3 degrees. Now, what would happen in this situation if we moved this ray? So if we move this ray closer to the normal, if we made this number smaller, what do you think would happen? So if we made our angle of incidence less, this one would probably go closer and closer to normal. But what happens if we make it farther out? Could it keep bending and bending and bending forever? Well, let's see what happens. We're going to do this diamond and water again. Right, so we're going to do diamond and water again. Diamond at 2.42 and water at 1.33. Here's our barrier. Here's our normal. What happens if we put this at, let's say, an angle of 60 degrees? So theta 1 is equal to 60 degrees. Let's see what happens. All right, so we write out our formula. N1 sine theta 1 is equal to N2 sine theta 2. So we get 2.42 times sine of 60 equals 1.33 times sine of theta 2. All right, so we do start off with that. 2.42 times 60 sine equals, we get 2.0957 is equal to 1.33 sine theta 2. We divide both sides by 1.33. And we get 1.5757 equals sine theta 2. I'm not rounding those. I'm just keeping my whole number on my calculator. I do second function sine, and I get an error. This is appropriate. We get an error. What that means is this light ray will not enter the water. It will totally internal reflect. Totally internal refraction. Oh man, that writing's awful. That means that this light ray will not exit. It will just reflect back into the diamond. So it will reflect back into the diamond with its reflection angle 60. So it reflects back into the diamond. So that's total internal refraction. So it did not leave. So there's a certain angle for diamond and water. If it's less than that angle, it will refract out. But once it gets to be that angle or bigger, it will no longer refract out. It will reflect back into the diamond and won't go into the water at all. Then this will act like a mirror, basically. Right, this is how fiber optic cables work. Fiber optic cables is basically a cable of glass. And they shine lasers in it. And the lasers hit the edge of the glass. And because they hit it at such a narrow angle, they don't refract out. They keep going along inside. And they keep bouncing back and forth on the edges of the glass. And they never leave. That's because the angle on the fiber optics is so small. Fiber optic cables are very thin. They need to be thin so you don't get a big angle here. So you keep the angle really, this angle with the interface very small. A very big angle with the normal. All right, so this is about refraction. Now, in this situation, you should also be able to solve for n in one of these formulas. But that's just a simple algebra problem that by the time you're in grade 11, you should be able to plug in a number here, figure that out, plug in a number here and here, figure those out, and isolate your one variable. It's not something we have to go over, mainly because I don't have an example that would work out well. So that is what refraction is. Refraction is when light bends going from one medium into another. And this is very important for lenses, magnifying glasses, phone lenses, telescope lenses, microscope lenses, glasses lenses. The light goes from the air into the glass and bends. And the shape of the lens and the material of the lens refracts the light different amounts to what we need it to do. Okay, so refractions is a very practical subject matter. Right, so if the light travels from a low-end material to a high-end material, it will bend towards the normal. If it travels from a high-end material to a low-end material, it will bend away from the normal. If it goes from a high-end material to a low-end material, and the angle is a certain size, you might get an error, and that means that it'll bounce back. All right, I believe that's all for this section of refractions. In the next section, we'll look at how to do ray diagrams for lenses. All right, if you have any questions, please ask. Thank you for watching.